All right, well, welcome everyone to our Design Master training. Today we are going to be looking at motor calculations in our Revit software to see how you can handle that. In your Blizz interface, there is the chat box, two little chat bubbles. If you click on that, it'll pull up the chat section where you can type in questions. So if you have any questions as we're going, you can type them down there, and I will answer those questions when I get a chance in my presentation. So we'll talk a little bit about motors, how those are handled in Revit with our software. Then there will be time at the end for you to ask additional questions related to motors or anything else Revit related that you'd like to talk about. So go ahead and get started here. I'm going to go ahead and click on this cooling tower here that's in my Revit model and run the instance edit command on it with the Design Master software. And so Revit does some stuff with motors, but not a whole lot. So we're trying to, again, as always, kind of layer on top of what they're doing. So Revit can, I think, do the motor calculations at the feeder and service level, giving you 125% of the largest if it knows that something is a motor. But otherwise, it doesn't do anything with the fact that you've got motors in a project and they need to be handled a little differently. So with Design Master, there's a couple things that we do. One, we size the breaker and the wire size correctly based upon the motor settings. We also include the motor contributions in your fault calculations, and we can display the motors on your one-line diagram. So those are the couple of things we'll be looking at here. When you run the instance edit for a branch circuit device, you have the option, and it will show the FLA, the MCA, and the MOCP for the piece of equipment. So if it's a motor, you're going to want to fill those in. And you can fill those in two places. You can do it here in the instance. So if you have just something in your project that you want to add those values to and then size breakers and wires based upon them, you can just open it up and set the values directly. You also can modify your families themselves. So if I run the edit family command in Revit, and then in Design Master, run our family edit command, we can define this family to be, switch it from a branch circuit device other to actually an equipment connection, which brings up a couple more options. And then here, we can specify the FLA, the MCA, and the MOCP so that when the family is inserted in the project, we'll see those values and they'll be pulled in automatically. So which you choose to use is a question of where you want to make the settings, if you want to modify your families and have this stuff populated ahead of time, or if you want to just modify it in your project, depending on how much information you actually know about the families and when you're getting that information from your mechanical engineer, because they're typically driving the sizes of a lot of these pieces of equipment. So looking at these values, we use them in the breaker sizing and the wire sizing. And those, the breaker and wire sizing point back to specific areas in the NEC that we'll take a look at. So we're basically trying to handle NEC 430, which is for motors, and then NEC 440, which is for motor compressors. So we've got the distinction there in the two different types of calculations. So starting at 430, motors, those for their breakers are based upon the full load amps on the FLA value. So if you have a motor, you'd want to specify the FLA provided by the manufacturer from your cut sheet. And then for your breaker sizing, choose one of these options here for sizing based upon that. If you go to 430.52, which I'm going to pull up here myself so I can quote from it properly. So I'm flipping to 435.2 in my NEC. This is all about the ratings and settings for individual motor circuits, and it has a table for sizing the breaker, and it's based upon a certain percentage of the full load amps, and it depends on the type of motor you have going on. So you basically need to go in there, look at it, figure out which section of that table you're in, and then choose the appropriate choice in our software. You can set it to 175% of the FLA, 225, or 250, depending on whether you've got a dual element fuse or an inverse time breaker happening. So you can make your choice there, and then we will size based upon that. The other option we have for breaker sizing, actually no, let's finish motors, and then we'll go look at the motor compressors. So for wire sizing, for motors, those are usually, there's nothing in the NEC specifically about sizing those. Those are all motor compressor exceptions for the wire sizing. So you typically are going to size your motor wire based upon the loads. So for this first option, typically we size our wire to match our breaker size. And so for most things, that's how you want to size it. Motors are a little different because your breaker is usually larger based upon that 250% of the FLA, and you don't need a wire that big. So you can actually have the wire be smaller based upon the loads. So if you choose up here in the breaker, say this is a motor, then the automatic sizing, the default, is going to size it based upon the loads if the breaker is based upon the motor. So we'll size it based upon the loads rather than the breaker in this case, because our breaker is based upon the motor. So we can set an FLA. I'll set it at 45 amps just so that we can see what happens when we set that. So for motors, you're really sizing based upon the loads. You can always override that to either say specifically do it on the loads or on the breaker if you want to do that, force a value there. So let's make these couple changes here, and then just go take a look at what all happens in the project before we move on and look at the other settings we can change. When you make your changes to your model, to your family, you need to load it into your project. I'll overwrite all my settings there. So if we go to the instance edit for this family now, previously we had a bunch of zeros. Now, since it's defined in the family, the FLA and the MCA and everything else is being pulled from that family. By default, it pulls the family value. You can always override it also. So if we set something in the family, you can still, at the instance level, override it or leave it to the default that's being pulled from the family. So we'll leave everything being pulled from the family, and we'll go look at our circuit definition. And here, you see that the breaker, we set our FLA at 45, which is going to make the math more complicated than I meant it to be. So we get 250% of that, so that's why we're getting the 110 amp breaker. But then the wire size is being based upon the loads. So it's going to be, I happen to notice, a 70 amp load on there, so it's giving us a 70 amp wire. We can go back and we can make some changes here in the instance rather than going back to the family if we want to override it here. So let's look at the motor compressor values, the NEC 440. So if you go over to NEC 440.22, which again I'm going to do so that I can quote properly from it. Okay, so this is specifying the size of the breaker, the overcurrent protection for your motor compressor. 440.22 it says don't exceed 175% of the branch circuit selection current, or 225% if there's these other things happening. And basically, you have to tell us which you want to use. So for your breaker sizing on your motor compressor, you need to go read the code, figure out which area you're in, and then choose the appropriate one. And we'll have it be less than that, and we'll also use the MOCP, and between the two, get the maximum value. So the FLA, it also has that BCSC, which is the branch circuit selection current, which is just way too long to actually fit in the dialog box, so we had to shorten that one up. That's not a common abbreviation in the electrical industry, we know, but we had to do that just for room there on that dialog box so that all fit. So for a motor compressor, we can size based upon those. And then the wire size, there's two options. You can size it based upon the MCA value or based upon the branch circuit selection current. And that's based upon whether you have a single motor compressor that has the branch circuit selection current, or if you've got a combined multi-motor happening where you have an MCA value in the cut sheet, and you just specify what that MCA is. So if we come here, and then if we set our MCA, we'll now have a 50 amp wire. If we set our MOCP, it's going to size based upon this. So that's where you can set those values, and then when we do the sizing in the circuiting, we'll be pulling those values. There's also the motor multiplier and the motor XR ratio. At the instance level, you can't change those. We left those in just the family because typically these are not ones you're going to be changing terribly much. So we didn't add all of the framework to do that because we didn't think people were going to be using it very much. These two values that we're looking at here are used for fault calculations. So if we go back to the family, we can actually make the changes there. So this is where you can set your motor multiplier and your motor XR ratio. So these are the motor multiplier is when there is a fault. We take the motor load and we multiply by this multiplier to get the load that the motor is going to be putting on the system for calculating the fault. The recommendation, kind of the default, if you look at the IEEE manuals, is 4 is typically what it's going to be. It's going to be the load's going to be 4 times the motor. If you happen to know, have a different value based upon a specific motor, you can override that. But if you don't know and you're just doing a standard project, commercial building, 4 is going to get you what you need. And then the motor XR ratio is, again, the XR ratio that's going to be used in the fault calculation. We have a default of 5, which for most motors and most commercial buildings is going to be appropriate. But if you happen to know that you've got a motor with a different XR ratio, particularly a larger one, you can override that here so that when that fault from the motor feeds back into the system, it's got the right XR going with it. So that would have to be a particularly large motor for it to really make any sort of difference. So again, for most commercial buildings, the defaults here are going to be sufficient. And those motor loads, there's one more thing you have to do to get the fault calculation as a motor load. On your connector in your family, if you select the connector, I've lost my properties. Let me pull up my properties in Revit here. I can remember how to do that. View, user interface, properties. There we go. Click on the connector. So in the properties, there's the load subclassification motor setting, which is a standard Revit setting. You need to check that on the connector for your motors in order for it to be seen as a motor in the fault calcs. So that's where we pull whether it's a motor or not for the fault calcs. It's separate from what we're doing here in the family edit. So here we're sizing it as if it's a motor. but you also have to specify it as a motor in Revit for it to be seen in the fault calcs. You also have to specify it as a motor here for Revit to see it for its load calcs as well. So we're assuming that you've done this and that you are doing it. So hopefully you are specifying your motors this way. If not, go into your families, make this setting here. So once we've checked that box, we will load this into the project. And if we go look at our fault schedule, I'm going to, we have just the fault at the device, and this is the fault, I believe, yeah, and that's the one including the utility and the motor fault. I'm also going to insert a couple other fault values here. Fault just from the utility and the motor fault. So I'll push those up so that we can look at them all together. Then we'll run our calculation, and I'm going to set a starting fault for this as well. So we'll say that we've got 65,000 amps at the utility, run the calculation, and now it's going to fill in all our values, both the fault from the utility and the fault from the motor. So in our fault calculation, the C column is the fault from the utility, so it's the 65,000 amps carried down through the system based upon the resistances of your wires and everything else. The motor fault is the fault from whatever motors happen to be in the project feeding back into the system. There's only one in this project that's connected to the CTP panel, so it comes into there and then just kind of goes out from there. So this is your total fault of all of your motors. And then the fault at device is the utility fault plus the motor fault added together there. So that's the total fault that you're going to see when you have a fault in the system. So those values are available as fields that you can include if you want to for your scheduling purposes, depending on what your planning reviewers want to see and what you want to specify. The last thing I want to point out for motors is that you can include them on the one line. In the instance edit, in the family edit, we have the show on one line diagram setting. So by default, all branch circuit devices are not shown because you don't want to show everything. But for your larger motors or other pieces of equipment, you come in here and you specify that yes, this thing should be shown. And you can either do that at the family level as everything else is done, or you can do it at the instance, depending on if you want to show just one of those or all of them. So if we say yes, this will show up. And then when we do our export in our one line, it'll show up there. So we'll go ahead and export our one line diagram. And I don't have AutoCAD loaded, so we'll get AutoCAD loaded while that does the export. And then we'll see that that piece of equipment does show up on the one line diagram in AutoCAD. So I'll put the one line diagram in there based upon our Revit model. And this is the CTP panel here at the far side with the piece of equipment connected to it. So that's how you go about showing your motors on the one line diagram. Didn't come into any labels, but we can come in here and we'll put the circuit on there just so that we have some label on it. And that is what we have for motors in Revit. Are there any questions on that, how those calculations work, the settings that we have, what you can do with our software? All right, I am not seeing any questions, so we will go ahead and end this class for today. Thank you all for attending, and we will talk to you next month, next year. Need to come up with my topic for next year. But we'll be looking at more Revit stuff next year. So if you have any topic suggestions, you can email them our way, or we will keep randomly choosing features and going over them.